In a universe shrouded in mystery, where the stars are our only companions, a journey awaits that will push the boundaries of knowledge. Prepare yourself for something that will redefine our understanding of technology, unveil the secrets of the cosmos, and witness the marriage of human ingenuity and artificial intelligence. We bring you the flagship event of IEEE SIESGST, the Galaxy of Intelligence, Epsilon. A triad of scholarly symposium days guided by the wisdom of global pioneers and visionary minds. An event designed for everyone to gain knowledge and cultivate interest and curiosity. In this edition, we give you Narrow AI. Narrow AI is the concept of brainstorming events that have a significant impact on AI technology, with humans like us, you, and me. We're not different, we are the same, with faraway souls. The concept of AI extends from the tip of your hair to the last cell of your nail. Computer vision. Computer vision excels in a field where robots outperform human vision. We will construct a future, the light of invention, together. Self-traveling dreams during the day and night. Algorithms flare in this world of pixels, revealing faces and emotions in the darkest night. With each step forward, we go closer to the future, the promise of computer vision and an unending flight. Deep space communication. MTT-S ascends, passing across galaxies in its path. Deep space learning is a place where mysteries wait. As boundaries disintegrate, the cosmos is revealed. The brilliance of AI and technology, the resolution of a cosmos. We gather at Epsilon, brains eager and bright, in the light of AI to comprehend the cosmos. Prepare for an intellectual adventure like no other. Mark your calendars because the future awaits. Epsilon 2023 starts 30th September live on YouTube. Brought to you by IEEE SIESGST.
Good evening, and a very warm welcome to all of you joining on the second day of Epsilon 2023. I am Sahil Anzarlekar, serving as Technical Head at IEEE SISGST.
And I am Prashant Gupta, the Administration Head at IEEE SISGST. After the exciting session we had yesterday under the MTT-S track, I am sure everyone is left with a sense of wonder about the deep space network and our universe.
Absolutely, Prashant. Today, we are back with an engaging workshop focusing on system design for space communication. During this session, our participants will delve into various aspects, including signal chain and system parameters, radars and communication systems, digital architectures, UAVs and drones, and space communication.
After the workshop, we'll have a quiz to test your knowledge and understanding of the workshop. Each question you take will contribute to your score, so participation is a key to climbing the leaderboard.
We hope you share enthusiasm for today's event. Without further ado, let's extend a warm welcome to our speaker for today, Mr. Archishman Guha. He brings a wealth of enterprise to the table. Mr. Archishman Guha is a field application engineer at Analog Device, specializing in high-speed data converters for aerospace, defense, and space technologies. He holds an MTech degree in space engineering from IIT Indore and a BTech in electronics and communication engineering from Kalyani College of Engineering. Beyond work, he enjoys football, swimming, and reading novels. Mr. Archishman Guha collaborates with organizations like ISRO and DDRO on next-gen tech projects.
Hello, sir. We are honored to have you with us today, and we are eagerly looking forward to your workshop.
With a great
Hi all.
anticipation, hello sir, welcome.
Hello. Welcome. Thank you.
With a great anticipation, we now hands the session over to Mr. Archishman Guha, who will share his knowledge and insights with all of you. Sir, you can take over.
Sure. Thank you all. I thank Sahil and Prashant for the generous introduction. And with that, I would like to thank the entire team of IEEE SIESGST for giving me the opportunity to speak today. First of all, after the intro, as I've been introduced, I work in Analog Devices, and Analog Devices is a company, just to introduce, that works closely with our nation's organizations to cater to our various defense, space, and our aerospace needs. Especially because I work with the high-speed converters and the ADF division, I would like to talk today about space communications and the various system parameters, the components, and what are the parts that we should be looking forward to design signal chain or the backend electronics of our space communication systems. With that, I would like to start. And hello, am I audible?
Yes, sir, you are.
Okay. So shall I present my screen, or how do you want to?
Yes, sir, yes, sir. Sir,
Okay, just give me
there
one
was one
minute.
request. Can you please turn on your camera?
Yes, just 1 minute. Let me find my link. I'll share the screen and then turn on the camera together. Is that fine?
Okay, sir, okay.
Okay. Is my screen visible?
Yes,
Hello?
sir. Yes, yes,
Okay.
sir, your screen is visible.
So basically, I would like to first start by introducing what is an RF system. An RF stands for radio frequency. An entire RF system can be very simply put as a solution to transmit and capture EM waves. Like whatever EM electromagnetic energy that is in our surroundings, if we can capture and process them in a right manner, we can actually transmit information through information from and to like a point to point communication system. This usually involves antennas, filters, transmission lines, ADCs and DACs that come under these high-speed data converters, and digital backends, that is your baseband processor like an FPGA or a processor that will finally hold the code or your scripts to run your end application. And this is RF is basically the entire radio frequency span is divided into frequency bands, as you can see. Like I have put up a picture from Encyclopedia Britannica that basically shows the divisions of the entire RF span. Moving ahead, a typical RF system would first, from starting from the left hand side of the screen, as you can see a dish antenna. It starts from a dish antenna, then it is followed by RF front end. These are parts that fit in right after the antenna, and they usually include low noise amplifiers, power amplifiers, filters, mixers to down convert, and I mean such ICs. The important parameters that you should be looking in your RF front-end design is the level of reception, that is how sensitive your front-end equipment is. Amplification should be optimum for your data converters, that is you should be amplifying. See, reception in your antenna would be at a very low level as in a reception power level would be very low. How much do I amplify so that my data converters can capture my signals properly and thus transfer it back to the backend for end applications. The pass band, stop band attenuation, as in like you've put in a filter, the filter has to be chosen in a right manner as to the filter should pass all the frequencies of your interest and try to stop or rather attenuate the frequencies that you are not interested in. Secondly, linearity. Linearity is basically, say you have a system and I say it's very linear. This means that the transfer function should be a straight line. If my transfer function has higher order terms, say to square terms, cube terms, then I would see other frequency components near about my frequency of interest, and that would cause a problem. Next up, I come to the data converters that basically contain the ADC, analog to digital converters, DAC, digital to analog converters, PLLs, phase lock loops, and clubbed with clocking. So this entire thing is basically trying to convert my analog data from my RF front end to a digital domain so that it can be seen and processed by my digital baseband. What are the important parameters that I should be looking here? I should be looking for resolution of the ADC. Whether shall I go for a 12-bit ADC, a 14-bit ADC, or a 16-bit ADC? That entirely depends on my requirements of SNR and how fine do I want a resolution. The sampling rate. The sampling rate is basically I should try to basically keep my frequencies within the first I mean Nyquist zone, but in the end I'll show you how now technological advancements have been made into the ADCs and DACs so that we can sample even signals that are far away from the first Nyquist zone, that is through aliasing. I'll show you how to do that. Instantaneous bandwidth, say you are interested in a span of say 1 gigahertz. You have to make sure that the ADC or the DAC IC that you're using can basically capture an instantaneous bandwidth of 1 gigahertz. So if you choose a IC that is able to only capture say 500 megahertz, you are going to miss out on information. So to take care of that, you have to be very careful about the instantaneous bandwidth that you are choosing for your ADC or DAC IC. Jitter in clocking. I'll explain what is jitter. I'll basically draw and like I'll use a notepad and try to explain what jitter is and how it affects my SNR. Jitter is basically the random shifting of the clock sampling clock edge, because I mean these are analog systems and there is supposed to be some amount of noise, though we'll try to minimize the noise. Because of this noise, the sampling edge of my clock might come say in a random manner, might not be very deterministic as to with respect to its location. It might come say a few femtoseconds on the left, few femtoseconds on the right. I mean randomly. That's where it's random. And finally, the digital processing on the chip. Now with the I mean I'll show you the analog devices IC architecture. You will realize that a lot of digital processing applications have been put within the data converter itself. So you have to basically decide what kind of digital processing do you want your chip to do, what kind of digital processing do you want your FPGA or your baseband processor to do. Also, finally, the communication protocol. The communication protocol is very important because this communication protocol would be the final bottleneck as to how much bandwidth you can capture. Say if you're using a LVDS or a JESD based communication protocol between your data converter and baseband, you would be basically limited by the amount of lanes, that is the number of output pins, output input pins, then the data rate, and also the power consumption. So these all parameters come into the picture when you have to choose your communication protocol between your data converter IC and your digital baseband. Finally, coming to the digital baseband, this digital baseband basically consists of my baseband clock. See, you see that there's a clocking in the data converters side also and the baseband side also. Clocking on the data converter side usually means the sampling clock. Okay, and on the right hand side, the clocking in the digital baseband is basically a digital clock that basically drives your digital systems in your baseband, because it's a digital system. Digital systems usually consist of FPGAs, known as field programmable gate arrays, where you can implement your final application. That is, the data that you receive from your data converters goes into the FPGA, wherein you run your final application. Now, again, the important parameters here: baseband data rate. It's because, see, it's a digital system, and if you were to run it at a very high speed, you need a very fast clock. And if you put in a very fast clock in a digital, simply put, if you put a very fast clock in a digital IC, you would realize that the setup and hold margins are very tough to manage. Henceforth, what is the baseband data rate that you should be targeting based on your frequency of interest? The application algorithm, what kind of an algorithm do you want to run on your FPGA, that is your baseband, syncing with the high speed converter IC. This is very important, because say I am sending a packet of data from my converter IC and I expect this packet to be received in my digital baseband. If there's no mechanism of syncing in between them, then these data bits would be absolute garbage by the time I receive it on the FPGAs, because they would not know, my digital baseband would not know what is the starting bit and what is the stopping bit. So it would not be able to make head nor tail of the data that is receiving, and finally the data that I receive on the FPGA would not be of any use to me. Now, another thing is very important part, capability, that is resource utilization. Say I want to do a simple FFT. Well, I do not need a very expensive FPGA. But say I want to do an entire radar application, a big application. That way I have to be very careful about the FPGA that I choose. Because if my FPGA does not have the resources that I need for my application, then there's no point of choosing that application. I need to choose a FPGA that has a very large resource bank. So this is an introduction of how a typical RF system looks. Now we'll basically pick out specific topics and look into the architecture of how communication systems look like. Okay. So these are some RF front-end parameters that I would like to introduce again. The frequency range is something that we are going to concentrate on a lot. The gain, S11, S21, S11 and S21 are basically the gain and the reflection losses. The insertion loss, that is amount of loss that you incur in a signal that passes through your system. The P1 dB is basically the input power at which the gain of the system drops by 1 dB. Then it's linear range. IP3 is basically, as I was mentioning, where does IP3 come from? IP3 comes from non-linear terms in the transfer function, say a cubic term. This would include frequencies that fall very close to your frequency of interest and thus corrupt your data. So how does this occur? The IMD2, how intermodulation terms are formed. I'll talk about them in the later stage of the presentation. See, now coming to space comms and telemetry. What you see on a screen is a very simplified diagram of a communication transmit link. And by transmit, I mean that when we are transmitting from say one point to another, we need a group of electronic ICs that can help me do my transmission of RF waves. So as you can see, starting from the right hand side of the diagram, you see the DAC, and the DAC is being fed with digital data. Okay, this digital data comes basically from my backend, my backend digital processor. We'll not talk about that right now. So just take it for granted that my DAC sees digital data from my baseband. Then I have an LNA that basically is a low noise amplifier. It basically amplifies my signal. And then you see a SPDT switch. SPDT switch is a single pole dual throw. They basically enable you to direct the path of my RF signal. So let's not talk about that right now. That's just kind of a, it just helps me guide my RF signal to a path. If you see it's on the at its current position, it will just directly put the LNA signal as the output. But if I were to switch it below, then it would be giving this signal to the input of the mixer. So what does a mixer do? It basically helps me place my signal of interest at the frequency band where I want it to be, and again an amplification, and thereafter to my antenna. Okay, so this is how an usual TX link looks like. uh, Again, I'll repeat, the DAC is basically transforming my digital data to an analog version. The LNA is basically a simple amplifier, and then comes my mixer that basically helps me position my signal at the frequency band of my interest. Say my communication link or links TX link works at a frequency of 2.1 gigahertz. My baseband is say around 100 megahertz. How do I put this 100 megahertz to 2.1 gigahertz through the mixer? I upconvert. Okay. So moving on, this is the RX link, which basically looks very similar to the TX link, but there are a few changes. If you see, the direction of the signal is the first change that you'll notice. This time, the antenna receives the signal through an LNA. Again, this time the mixer helps me to down convert. So I have a very high frequency signal. Through the mixer, I down convert. Then I feed it to my ADC, which then feeds it back to my digital baseband. This is an Earth observation payload. As you can see, on the left hand side, you will have an rotating switch that basically helps me to switch between my receiver and transmitter array. This is also very similar. It's just that the signal chain almost remains the same, wherein you just see a driver in the transmitter array. Driver is basically, I mean, you can a bridge between the mixer and the power amplifier. A power amplifier is nothing that has like a high gain, and it will be able to output a high amount of power through your antenna. On the downside, if you see on the below, you see clock and synthesizer block. What does this do? This basically generates my all the clocking needs for my entire arrays. Say my digital clocking, my ADC clocking, and my DAC clocking. Okay, and these basically are driven to my transmitter and receiver array as sampling clocks, or for that matter, I'll also talk about some other digital clocks that are also needed at times. So this is also something similar. This is the command and telemetry. As you can see, like there's also a calibration monitor in unit that basically, what it does is it's basically senses the temperature and all. This is not of much interest to us now. What I'm trying to concentrate here is about the telemetry uplink and telemetry downlink. That is where the main RF goes through. Again, same as before, the clock and synthesizer block is basically generating my clocks for my sampling. Moving ahead, now I would like to introduce radars to you. So radars are basically a system, a solution that helps you to detect ranges through RF waves. So usually what happens is you have an antenna. Okay, you have a phase shifter starting from the right hand side of my diagram, and then you have some amplifiers. Are you I hope everybody is able to follow, right? Okay, so essentially what happens is this phase shifter is there, right? It will be basically a phase shifter. It will in the analog domain, it will give a phase shift. What I want you to concentrate on is after the LNA, what you see is a mixer, that is again a down converter here on the ADC side. You have a driver amplifier. This is the IF amplifier, as you all know, intermediate frequency, and then to my ADC, and then off to my FPG, right? This is how the typical simple radar system works. On the DAC side, it's very similar again, that you have the DAC generating the digital analog data from the digital, that it is from the DSP or the FPGA, then it up converts to the mixer, and then it feeds it to the antenna. Now, as I was saying that for these applications, for radar applications, for electronic warfare applications, you need a very wide bandwidth. So what we are trying to do here is we are trying to implement a direct conversion radar. As you can see, the difference is the number of front-end elements have been reduced from the previous slide. If you can notice that the number of front-end elements here, okay, this IF based system has been reduced, uh, by a large number in the direct conversion radar system. This is because now we've been able to design converters that support a very wide band, and henceforth you can, since they can sample a very wide band signal, you can do away with a little bit of front end modules. Now moving ahead, this is how a direct conversion radar basically looks like a very simple version with only one transmit chain and one receive chain, then we'll be moving on to phased arrays. Now, what is phased array? It's basically, say, if I were to take a large number of antenna elements and then give a particular phase shift, what I claim is that I can turn the antenna beam towards a desired direction. Now, you would ask me that how does only phase shifts alone give a rise to a beam that I can basically make them beam move around a desired direction? I would urge you to read on this topic. I have to put it very simply. What happens is, since you are giving a phase shift to the waves, EM waves, they constructively interfere at some locations and they cancel out each other at some other locations. The region where they constructively interfere, they add on one top of one another. That's where your beam exists, and that is the direction of interest. That is where you'd be either transmitting or receiving your signal from. So now essentially what happens is, say, as you can see in the diagram, I have antennas and I have given a phase shift of phi, delta phi, gradually to all of the antenna elements. And as you can see that there's a beam that is being pointed towards a direction from an angle of theta from the perpendicular. So essentially there's a lot of math going on. As you can see, there's a small formula right on the right hand side. Delta phi is equal to 2 pi d sine theta. It basically determines, if you have your delta theta and you have the d, that is the distance between your antenna elements, and lambda, which comes from the frequency of the signal, you'll be able to calculate the theta, that is the angle at which your beam is basically pointed at. And what we will try to do is, we will try to mimic this entire system digitally, and henceforth what we'll have is a digital phased array radar, wherein we'll be able to control all our parameters, say gain, phase shifts, everything, the frequencies, digitally through all our digital blocks rather than going for analog blocks. So a small comparison, as you can see from the left hand side of the diagram, that says that's an analog beamformer. What you see is that there's an antenna array, and the focal point is basically the region where my beam is pointed at. Then the yellow blocks are the variable delays. These delays are basically responsible for giving the phase shifts. Then I have a summer, and then I give it to my ADC. Okay. On the digital side of things, what you would notice is, before the FIFO, that's the first in first out array, where I give my variable delays, I sample the signal. So there's a difference between the digital beamforming and analog beamforming. Okay, so this architecture in a very simple way tries to summarize how a digital beamformer would be different from a analog beamformer. So basically, this is a very generic diagram. I would like to just discuss how things are basically placed in a phased array platform. First of all, beam data, which is of course digital. Then you have your digital beamformer, wherein your digital IC is responsible for giving your phase shifts. And if you notice, there's a arrow sign with a like a register mark. That's basically a variable attenuator. And then you have an equalizer. We'll not talk about the equalizer right now because it's out of the scope of this presentation. And then the digital up and down conversion. The digital up and down conversion is very similar to what we just discussed about with the mixers. They help us place our signals in the frequency band of interest. Okay. And then you again have your analog up conversion. This is the digital up conversion, which is through an NCO. I would like to specify, NCO specifically means numerically controlled oscillators. So how does a numerically controlled oscillator work? If you want, I'll discuss that too. And then we move on to the analog up and down conversion, wherein we use an LO, a local oscillator. On the digital side, we use an NCO. Here we used a local oscillator, that is an LO. Then you have your analog beamformer with your analog attenuators, with your phase shifters, and then you have your transmit and receive modules. So if you remember that what I mentioned was that this intermodulation products, if you notice, say I have a two input tone. Tone basically means there are two frequencies, say F1 and F2. What I mean is that if I were to pass this signal through any of my say amplifier blocks, or any of my any of my ICs, RF ICs, they were to produce two extra frequencies, 2F2 -1 2f1 minus f2. These are basically my intermodulation products. Okay, these are, I mean, 2f2 minus f1 and 2f1 minus f2 are my intermodulation products. And if you notice, these intermodulation products lie very close to the signals of my interest, that is f1 and f2. So essentially, a system that has a high intermodulation product power, say the power levels of 2f2 minus f1 are very high, then what is happening is you are basically corrupting your frequency band of interest. Okay, this is something that will basically hamper the performance of your system. Next up is the intercept point concept. Okay, so basically what happens here is, as you can see, the P out and P in starting from a very low power, it is a straight line, means the system is linear out there. Then you notice that there's an amplifier compression curve. This means that beyond this power level, your amplifier is no longer linear. And by linear, when the amplifier is no longer linear, then I will of course have my non-linear terms, and this is exactly I don't want non-linear terms to be in my equation of signal processing, because non-linear terms would give out like my higher order terms, my intermodulation products, and therefore I'll end up corrupting my frequency of interest. Okay, so these are some receiver architectures that I want to just introduce to you all. So heterodyning is basically, first you pass your signal of interest through a bandpass filter, then down convert it to an through an LO, and then you feed it to an analog to digital converter. And if you notice that this analog to digital converter, okay, can be done at a lower clock also, because here what you are doing is, here you are basically pushing your high frequency signal to a low frequency before you sample it. So if the frequency is lower, I mean the sampling rate of the analog to digital converter would also be lower. You can afford to keep an analog to digital converter that is able to capture at a lower sampling rate. Also, there's an direct conversion architecture wherein if you see, the received analog signal is being passed through an LO that is 0 phase shifted, and on the below side it's 90-degree phase shifted. So if my LO is a cos, I would multiply my signal to I mean if my LO is a cos, I would first multiply the RF signal with a cos, and on the bottom side here I would multiply my RX signal with a sine. This basically generates IQ samples, and these IQ samples have to be simultaneously sampled by two AD converters. Of course, the advantage is that I have a wider bandwidth, but then again, you notice there are two ADCs involved. Also, another issue is, see, these ADCs might not be identical. You might choose the same ICs, but there will be some amount of mismatch between the ADCs. So these mismatches finally get introduced into your IQ data, and then you have a little bit of IQ imbalance. I mean that this is a problem that you would face if you use two independent ADCs. Next is the direct sampling. The direct sampling is basically like you would not have any level of down conversion or mixer levels. You would just directly feed in your RX data to your ADC. Now, if you want to sample a very wideband signal, this analog to digital converter in the direct sampling architecture needs to run at a very high frequency. And this is exactly what we'll discuss in the next part of the presentation. Also, as you all know that this is basically an example of how the heterodyning direct conversion work. So just quickly running through it, if you notice that what happens on the heterodyning is, this signal of interest FC is basically down converted to the second Nyquist zone, and it basically aliases back into the first Nyquist zone. This aliasing is basically happening because of the sampling rate of the ADC. Okay, because if the signal lies on the second Nyquist zone, that is beyond Fs by 2, where Fs is the sampling rate of your ADC, you would see the images of your signal in the first Nyquist zone. The direct conversion, that is the 0IF, is what it does is basically you have an LO based like you put your LO at the center of your band. This LO basically shifts it to DC, somewhat like this. And with the digital direct sampling with down conversion, I'll show you through an architecture how this down conversion works. Okay, it's basically you have your signal of interest. then your NCO, it's basically you have aliased your signal to a point where the NCO is written, then you use your NCO to further down convert the signal digitally, and this digital conversion would happen within the architecture of your IC. We'll talk about this later. So this is basically an architecture, a very
Hello,
simplified
sir.
architecture. Hello, yes.
Sorry to interrupt you, sir, but can you increase the lighting in your room, sir? Your face is not clearly visible.
Okay. Just 1 minute. Just give me 1 minute, okay?
Yes, sir.
Hello, looks better now?
Yes, sir, much better.
Okay. Okay, my screen is visible, right?
No, sir, not yet.
Okay, just a second. I think so. It should be now. It's visible, right? Hello? Seems to be visible. Okay, so coming to this architecture, as I had been mentioning, that a part of the digital processing should be taking place within the a converter IC. This basically helps us to go forward with this direct sampling architecture. As I mentioned you in the previous slide, you'd notice that right after the ADC, I have a digital backend here, digital backend running within the IC. So this architecture is somewhat a solution to a wideband ADC converter that samples at a very high rate and then manages to send the data back through a very complicated, complex communication protocol, that is the JESD, to my backend. So allow me to explain. I'll take a little time here. Please try to follow this. See, I'll start from the receive chain first. As you see that this IC, which is the analog devices 809081, okay, this IC, you'd see there are four ADCs: ADC 0, ADC 1, ADC 2, ADC 3. Essentially, this means a single IC can sample four independent RF paths like simultaneously. So ADC 0, there are four ADCs each running at 4 GSPS, that is 4 gigasamples per second, which yields a Nyquist of 2 GSPS. You would see that what we have is one IC consisting of 4 receive, and on the top side you would see 4 DACs. That means that we have another 4 transmit channels too. This means a small IC of say this size, it's basically of this much size, can basically handle RF data into 4 TX channels and 4 receive channels, 4 transmit and 4 receive channels simultaneously. So this is where we are currently working at. We are trying to integrate more and more digital processing within a single IC, so that what happens is we can offload these digital processing algorithms from the baseband FPGA onto our chips, albeit trying to make the sizes of the IC small and small. So as I told you, the size is just this much, and you would have 4 receive and 4 transmit channels with the entire digital backend signal chain. You would see that right after the ADC, I will be having a router mux. This basically you can for now assume that it's just a data router mux. It just channelizes my data. I have a programmable filter too. This programmable filter, what it does is you can select the band of your interest. You can use it as an equalizer between your 4 channels. Also, you can implement various filters, basically digital filters, say a low pass filter, a band pass filter, or a high pass filter. Now the best part is this filter is programmable in real time through your SPI interface. So what basically the advantage of implementing all these filters, your NCOs, digital up conversion, down conversion, digitally is that you will be able to reconfigure them. Okay, for say you just need to as you all know that to design a digital filter you need to have some coefficients, say a 32 tap filter, a 192 tap filter, a 28 tap filter. So you'd have to just generate the coefficients, and you'd have to sorry, you'd have to just manage to push these coefficients into your chip through your SPI, and that makes it programmable. So the advantage is once you have your digital uh, receive chain, you will be able to digitally change your NCO frequency, your filters, your delays, etc. and etc. So as you can see, moving ahead, after the programmable filter, you have a delay adjust. This delay adjust basically will help you to introduce delays within the signal that you have received. And mind you, these are all digital delays. Now you have the coarse digital down conversion. This coarse digital down conversion is basically, it will allow you to down convert, basically set your NCO -2 gigahertz to +2 gigahertz. Okay, so this is a very wide band range uh, at which you can place your NCO at. Again, to add to the amount of down conversion possible, you have a fine digital down conversion that basically allows you to set an NCO frequency of up to 750 megahertz. So this is the entire amount of down conversion that you can have, and in a programmable nature. So this is the example of a very complex IC that I just wanted to simply explain to you how these wideband ICs work. Similarly, on the receive side, you'd see first you have the fine digital up conversion, which is again that the 750 part. Then you would have your coarse digital up conversion, which basically helps you to up convert at a larger frequency, say 2 gigahertz, and then you can output your signal through the DAC outputs to your RF front end. So essentially what happens is, what I'm trying to summarize here is, through a digital implementation of all these signal processing applications within a chip, we have introduced the ability to sample wideband signal and also put in the future feature of reprogrammability on the fly. Through your SPI, you can basically try to change the NCO frequencies. You can try to change the P fields. You can try to change the data rates so that you will be able to basically sample, say, a wideband signal or a narrowband signal, all in a programmable fashion. So on the right hand side, I'll just introduce to you very simple terms. As we discussed, it's flexible, reconfigurable, and 4 DACs, 4 ATCs is already discussed. See, data paths and DSP blocks are fully bypassable. This is another important thing. So now somebody might ask, okay, it's very good that analog devices has introduced so many digital processing signals, digital processing applications into one IC. What if I do not want to use them? What do I do? Our answer is simply bypass them. That's all. So it's basically you can bypass the entire DSP too. Okay. Now another very important thing is this on-chip PLL. What is an on-chip PLL? So basically, as you notice that what I was saying, the DAC will run at a clock rate of 12 gigahertz. Okay, and the ADC runs at a rate of 4 gigahertz. Who will generate these sampling clocks? Okay, I'll come to the point where we discuss how to generate sampling clocks, but for now just take it for granted. What happens is, to generate my 12 gigahertz, I need a mechanism within the chip that can generate the sampling clock for me. So what happens is, I have the facility to input a low frequency signal at this clock in and clock in ports. Okay, and this through a PLL, I'll have a higher frequency clock that will be basically used as my DAC and ADC sampling clock. I always have the option to choose to externally provide this clock too. Meaning, I might choose not to use the PLL. I might choose to have my own PLL IC, which is externally located on my PCB, and I would like to feed my sampling clock from an external source. That is also possible. Okay. Now, there's another thing that I would like to introduce. The last part of it, what I say is 7.5 gigahertz of analog full power bandwidth. What does this mean? This means that I can send in an RF frequency of up to 7.5 gigahertz without attenuating it, like basically without reducing its power by half. So what does a 3 dB bandwidth mean? It basically means the frequency point at which your input signal would be attenuated by half. The power would be attenuated by half. Now, the first question comes is that you said that I'd be able to sample on the ADC side at a frequency of 4 GSPS, 4 gigahertz, and on the DAC side, I would be able to sample at 12 GSPS. Now my question, like you would ask a question is, the Nyquist is at 2 gigahertz for the ADC and the Nyquist is at 6 gigahertz for the DAC. Then what do I do with 7.5 gigahertz? Right. This is a very common question that would arise. Okay, you are claiming to have given me 7.5 gigs of analog bandwidth, but your Nyquists are only 2 gigahertz on the ADC side and 6 gigahertz on the DAC side. How do I manage? What is the use? This is where aliasing comes in. This is where high-speed data converters, you can take the, I mean, the architecture of high-speed data converters, you can actually take the help of, uh, or rather leverage the effects of aliasing, that is basically capturing the image of your frequency of interest in the first Nyquist zone. Okay, so basically this is an advantage. I mean, this is also how you can use the chip, because it has a very wide bandwidth. You can actually be able to sample signals through their images which are far off from your I mean, which are beyond the Nyquist zone, that is half the sample rate. Okay, now as I was talking that I have to generate PLL, I mean, a high speed sampling clock. So this is a very simple PLL architecture, which basically stands for uh, phase locked loop. And for the example, for this example, I have chosen the architecture of analog devices ADF4377, which is a PLL that generates a frequency of up to 12.8 gigahertz. To concentrate, what basically happens within a PLL architecture is, and this PLL architecture is the sampling clock that I was talking about, this 12 gigahertz sampling clock, the DAC sampling clock. Where do I generate? This is a simple PLL architecture that helps me to generate a very high frequency clock. So I have a low frequency reference. This reference is fed to the ref P and ref N pins on the left hand side of my of the block diagram shown. This reference through a VCO, okay, is basically multiplied to a very I mean a very high frequency sampling clock, say 12 gigahertz for our example. Also, these PLL architectures have a very large amount of digital architecture within them. So again, this comes with a feature of programmability. That is, you can choose a frequency of 800 megahertz to a frequency of 12.8 gigahertz. So you realize the large bandwidth of clock that you can generate from only one single IC, all being digitally programmable. Okay. So I'll explain this again. Okay, I'll come back to when I start using my notepad again. First of all, I would just like to introduce you to the topics. Now, this is a clock IC. See, what is the difference between that a PLL and a clock? It's just that this PLL, okay, as you can see, this also will have a PLL, okay. But what happens here? The frequency is limited to only say 3 gigahertz, 3.2 gigahertz. I cannot go up to 12 gigs of frequency with a clock IC. What is the use of these? These are basically can be used as your digital clocks, say your FPGA clocks, say your JESD clocks. JESD is basically the communication protocol used by 89081, which was the a transceiver IC that I just discussed previously. These can be used as digital clocks. So how do I generate digital clocks? This is an architecture wherein you have your clock, say a reference clock through a PLL that transform this clock to a high frequency, say 4 gigahertz. From there on, if you see, you have this out 0, out 1, out 2, out 3. Through these, you can basically output clocks, and you can also control their digital delays. You can also divide the clock. And why is clock division important? Because say your VCO runs at a frequency of 4 gigahertz and you need a clock of 1 gigahertz. What do? You just simply switch on the divider and ask your divider to divide your clock by 4. And that is how you generate a 1 gigahertz clock from a 4 gigahertz clock. Okay. Now the advantage is, since you have so many outputs, right? You can output clocks of different frequency from different outputs, and also put in different amount of analog delays, digital delays. Now you'd ask me, what is the use of analog delays and digital delays? It's basically, say you have a PCB trace, okay, and there would be, like, say there's a PCB trace length mismatch. That is, your IC sits on one of the corners and the traces to your other ICs, okay, from the clocking IC is different. Okay, so how do you manage so that your clock reaches all the slave ICs at the same time? You manage through your digital delays. Basically, the paths which are shorter, you put in delays there to make them basically shift on the time domain and make sure that all the clocks are simultaneously received by my slave arrays. Okay, so this is a very this is the Quad MXFE platform. What is the Quad MXFE platform? Let me just go back. This is just one single IC, this 89081. Okay, now, what if we want a larger system? If somebody comes and tells me, okay, you have an IC that can have 4 TX channels and 4 receive channels, but what do I do if I want to have a 16, say 16 receive and 16 TX channels? Question number one, do I build a IC that basically will have 16 transmit and 16 receive channels? No. What do? I develop a system. I develop a system wherein I am able to synchronize. I am able to synchronize 4 of my ICs together in the time domain by synchronizing all their digital clocks, their baseband, their digital signal chain. I'm able to capture data in a synchronous manner through all of the 4 ICs, wherein I can also control in a deterministic manner their phase offsets too. This is how, from a single IC that has only 4 receive and 4 transmit channels, I am able to generate a fully synchronous, a power up phase deterministic synchronous system through my Quad MXFE platform. Okay, so how does this occur? Basically, it's a very complex system. I'll not go into the depth, but just to introduce, I'll first have to synchronize my PLL clocks, that is my sampling clock, to the DAC and ADCs. Thereafter, I have to make sure that my digital up converters and down converters are also phase synchronous. That is, they lie within the digital architecture of each of the 89081 ICs. And just to point out, the 89081 ICs lie below the fans that you see. The 4 fans are there, right? On the, just below them are the ICs. Okay. So point number 1 was the PLL clock synchronization. Point number 2 was my your NCO, that is your digital down converter and up converter synchronization. Lastly, I have to synchronize my digital baseband data. So, say very simply put, these are the 3 steps that I need to follow to basically synthesize a synchronous system with a large number of converter ICs. Okay. Now, these basically are parts of the backend electronics that you can put in your RF communication, that you can both use in your 5G, your space communication, your aerospace, your defense applications. Last up, since we've been talking about, these electronics, I would just like to introduce to you what are the effects of electronics in space. Okay, so I'll not take much time here. So basically, there are few sources of radiation, that is the trap radiation, the transient radiation, and the solar particle events. Basically, your solar flares and all that basically emit a lot of charged particles like protons, electrons, and all other radiative particles into our electronic devices, and they have numerous effects. What are the numerous effects? You would see that they occur single event effects. Okay, it's basically, say there's a high dosage of radiation to one of your registers. Your registers might get latched up to say a particular value. What might happen? They might get reset. They might even get like what do you call as single event latch-ups. It's basically what happens is, say you receive a dose of ionization or radiation within your IC, and what happens is you see that all your registers have gone to latch-up value, that they are all ones, they are all zeros. Basically, there's no data. It basically corrupts your entire system. Single event resets. What might happen is, say you have an IC and you have a memory device wherein you store all your data that you've been receiving. A single event of your radiation can basically trigger an entire reset of the memory. So these are basically some single event effects that your electronic ICs really are prone to in the space environment. And to put very simply, these are some challenges that for electronics in the space arena. Okay, so with this, I complete my introduction to all the topics that are required. Next up, I would like to move forward to basically use my pen and pencil to explain you some concepts. Okay, so first of all, I'll try to explain why this two-tone intermodulation product is very why do I need to really concentrate on it? Okay, so going back, I would like to use mine. Okay, so guys, do you want this to be black or is it fine? Okay, where are you? Okay, guys, Miss Notepad is visible, right? Can somebody just type it in the chat once? Okay, thank you. So basically, what I claim is that my signals, okay, say I have a signal at 500 megahertz, okay, okay, I have a signal, say at, hello, I have a signal that is at 500 megahertz, which is my F1, and I have another signal, say, which is at 600 megahertz, which is at F2, okay. Now, what is 2F1 minus F2? 2F1 would be 1000 megahertz minus 600 megahertz, okay, which is basically 400 megahertz. And what is 2F2 minus F1? It will be 1200 megahertz minus 500 megahertz into that is equal to 700 megahertz. So if my RF system has a higher level of power in the forms of these frequencies, say, what I'll notice is, say, if this is my frequency band, if this is my frequency band, and I see that these are my F1, this is my F1, and this is my F2, F1, F2, and what I would notice is that this 400 megahertz would come, this 400 megahertz would come somewhere very close to, because this is at 500, this would be at 400, okay, this is at 500, it would come very close to my F1. Also 700 megahertz would come to very close to my 600 megahertz, okay. So if I don't ensure that my RF system has a very low power, that is a very low intermodulation products, then I would basically corrupt my frequency band, which is very close to my signal of interest, this part, okay, because the unwanted frequencies in the form of 2F1 minus 2F2 and 2F2 minus F1 would basically lie so close to the frequencies of my interest that it would be very hard for me to filter them out. And henceforth, usually what we do is we go into parameters of this kind, that is your 2F2 minus 1 and 2F1 minus F2, okay. This is one like a concept that I wanted to emphasize on further. Next up, what we'll do is we'll move on to this part, okay. I'll mathematically show you what happens, okay. Since we all know that say I have an ADC that samples at say 1 gigasamples per second, that is a sampling rate of 1 gigahertz. So what would happen is, if say this is my 0 hertz, this would be my 1 gigahertz, and my Nyquist would be within 500 megahertz. Now my question is, what if there's a signal that lies at say 700 megahertz? What would happen? In the digital side of things, what I would notice is that this would basically, the image of 700 megahertz would basically lie in the first Nyquist zone. That is, when I were to digitally sample it, okay, digitally sample, I would notice what would happen is there would be a 0 frequency. Again, I put the 500 here, I go for the 1 gig here, okay. I would see a 700. Also, I would see a 300. Now, how does this 300 come into picture? Okay, so what would happen is I would basically have its image from the sampling frequency. So what happens? What is 300? 300 is basically 1 gigahertz minus 700 megahertz, which is my frequency of interest. And as I was mentioning, well, I want to just take you back to the point wherein I just mentioned that the 89081 has a sampling rate of 4 gigahertz, but I have an usable bandwidth up to 7.5 gigahertz. So what happens is very similar to what I just showed you, that we basically sample an image of the of the signal that is beyond my first Nyquist zone. So just to make things clear, this is how. So what I would see is on my ADC side within the first Nyquist zone, I would see 300 megahertz. And since I already made a calculation, okay, I'm sampling at 1 gigahertz. My signal of interest is at 700 megahertz. 700 megahertz is somewhere here. So I already calculated, okay, I should be expecting something around 300 megahertz on my baseband, and henceforth I'm interested on the image of my signal of interest. Okay, so now coming to the point, okay, say what happens is I have, now I'll just explain what is the use of the P filter. Okay, that's a very simple example. The programmable P filter, sorry, FIR filter. Okay, basically this is reprogrammable. You just need to generate coefficients and just reconfigure the IC through SPI. Okay, so what happens is, say now I have my, again I have my signal span, and this time we'll work at 4 gigahertz. Okay, 4 gigahertz is basically the sampling rate of my 80908. Okay, say I have, this is my 0 and this is my 4 and this is somewhere lies my 2. What I have is, I have a signal, I have two signals of interest. First one lies at say 3 gig, no sorry, let it be at 2.1. Okay, let it be at some 2.4 gigahertz. Okay, there's a first signal that is at 2.4 gigahertz, and also I am receiving some other frequency which is not of my interest, say at 3 gigahertz. Okay, 3 gigahertz. Now I would notice that what would happen is, I would notice the image of my 2.4 gigahertz 2.4 gigahertz at 1.6, because 4 minus 2.4 is 1.6, so it would be somewhere here. Okay, 1.6 gigahertz, and the image of 3 gigahertz would be from 4 minus 1, that is at 1 gigahertz. Okay, and its power would be something lower. Okay, this is the red one, and this is my pink signal. So now what if I want to eliminate this signal. Okay, I want to eliminate this signal. What happens is, what I'll do, I'll ask my programmable filter, okay, you program yourself with as a band pass filter, okay, with a pass band of say 1.5 to 1.7 gigahertz. Okay, so what would happen is, my filter would take a shape of something like this, say 1.5 to 1.7. Okay, so what would happen, due to the filter response, my the image of 3 gigahertz would be attenuated, and at the baseband side, what I would see is, I would see my signal of interest, that is the image of 2.4 gigahertz at 1.6 gigahertz, okay, as is, and I would see a very attenuated version of the signal that I don't want, that is at 1 gigahertz. Okay, so this is an example use case of how you can use your programmable filter too. Okay, next up, I'll go to my slides once. Next up, okay, yes. So just to reiterate, as you can see that after the programmable filter, I have my down converters. Okay, so essentially what is the point of using the down converters? I'll tell you. Now continuing with this example, okay, I was having a Nyquist of 2 and then a Nyquist of 4. Okay, now essentially what is happening, at until this point of time, I was sampling at 4 gigahertz. Okay, and my Nyquist was at 2 gigahertz. Okay, now what if someone tells you that I cannot take a Nyquist of 2 gigahertz because the data rate is too high, it's 4 giga samples per second, and to put it into numbers, this basically is 4 into 10 to the power 9 samples of signals per second. Okay, if somebody says, Okay, I cannot afford to have 4 giga samples running into my baseband. Say my baseband cannot receive such high data rate. What do? I use my digital down converters. I use my digital down converters to first reduce my frequency, and this is point number 1, and then reduce my data rate too. Okay, so basically I was having a frequency of interest at 1.6 gigahertz with a Nyquist of 2 gigahertz. Okay, that is a sampling of fs is at 4 gigahertz. Okay, sorry, okay. Now what I want to do is I'll tell you that, okay, I have this 1.6 gigahertz. I'll feed this 1.6 gigahertz to one of my down converter NCOs. Okay, this is an NCO. Okay, and I'll put it to say around 600 megahertz. So I'll down convert it by 1 gigahertz here. So as soon as I convert my signal from 1.6 to 600 megahertz, the Nyquist requirement automatically becomes here. If I want to sample a 600 megahertz, say, instead of sampling at 4, now I can sample at 2 gigahertz. Sorry, okay, now I can sample at 2 gigahertz too. So if I'm sampling at 2 gigahertz, my Nyquist has reduced to 1 gigahertz. So thereafter, what is happening? I had 1.6, I down converted it to 600 megahertz to an NCO, which is equivalent to a digital analog mixer. It is just a digital version. Now at the baseband, say this is my converter chip. Okay, this is my AD9081 and this is my FPGA. Okay, FPGA. Okay, here at this point I was having a signal at 4 GSPS, 4 gigasamples per second, but I did some digital processing, signal processing, to reduce this 4 GSPS to 2 GSPS on the baseband, so that my FPGA sees a lesser data rate. How did I do it? First, I reduced my frequency through an NCO to 600 megahertz, and because 600 megahertz is well within the Nyquist of 1 gigahertz, I could reduce my sampling rate to 2 gigahertz within the digital IC itself. Thereby, I solved the problem of having a 4 GSPS signal, reducing it to 2 GSPS without any loss of information, and entirely through digital programmable abilities. Okay, so this is how the chip works on a very basic level. Also, yes, next coming to the PLL. This is a very important one. Okay, how does a PLL work? So essentially, now coming to the PLL part. PLL basically stands for phase lock loops. Okay. So essentially, what is the aim through an PLL? The first aim, the first consideration is I will have a low frequency clock. Okay, a low freq clock. Okay, say 100 megahertz. Okay, I have a low freq clock. Okay, I have a low frequency clock. So what would happen is I would feed this low frequency clock, say a 100 megahertz clock, say a 100 megahertz clock, and I would have an internal VCO that would basically have a divider. Say I want to produce a frequency of 4 gigahertz. Okay, 4, or say I want to produce a sampling frequency of 12 gigahertz. What would happen is I would divide my VCO clock. Okay, and I would feed it to a phase detector. Okay, I would divide it. Say I need a divider of around 12 to the 10. Okay, so this has to be my divider value. What would happen? It's basically 12 3. So I would need to divide it by say 120. Okay, So what would happen is essentially I will have to first of all divide my 12 gigahertz to bring it down to 100 megahertz. This will happen internally within the PLL IC. Okay, where does this happen? I'll show you. So if you notice here in the like in the IC, if you notice here in the IC that this N divided is there, right? See, this is the VCO which is running at 6.4 to 12.8 gigahertz. What happens is after this clock divider, okay, I will route this clock back to the N int, which is the divider, okay, and this divider is basically fed to a phase frequency detector, which basically what it does is it basically, say I have my 100 megahertz clock, which is a very slow clock with respect to 12 gigahertz, and say I have my 12 gigahertz clock, which is a very fast clock. Okay, what it does is it basically calculates the phase difference, the phase error between these two clocks, that is the 100 megahertz clock and my 12 gigahertz clock. So what it does is it basically corrects for this error, okay, through a phase frequency detector and a charge pump, and then keep pushing the VCO down and up. That's a little complicated, will not go down too deep. So what happens is this PLL basically corrects for this phase difference between the rising edges of my 12 gigahertz VCO clock and my 100 megahertz and my 100 megahertz reference clock. Okay, so what happens is after the PLL operation, that is, we call it that the PLL has locked. This means that the phases, that is the rising edges of my 100 megahertz clock and my faster, say 12 gigahertz clock are basically phase aligned. This is the ideal operation of a PLL. So essentially what happens is from a 100 megahertz clock, okay, that is a low frequency clock, through a VCO based PLL, I generate my 12 gigahertz sampling clock. Okay, and the quality of this sampling clock will basically determine the AC performance of my RF. Okay, so, and is there anything more? Okay, so presently I see that I've completed most of it. Okay, and that is it. Okay. Hello, so I'm mostly done. Just checking if I may have missed out anything. Okay, I need to go through this clock architecture. So I'll now take you through this clock architecture. What happens is now a clock architecture is basically, you can assume it that say I have a clock IC, I can distribute such low frequency signals to multiple PLLs because I have a large number of outputs. I can basically output a large number of say 100 megahertz clock signal or say a 1 gigahertz clock signal in a phase aligned manner. Say for example, what happens is the ability of this clocking IC is, say this is my clocking IC, okay, and this is PLL1 and this is PLL2. Okay, this is PLL1 and this is PLL2. I route one of the outputs of my clocking IC. Say the name of the clocking IC is an LTC6952. Okay, which is an analog devices clocking IC. What happens? I route different length cables to two of my PLLs. That would be generating my 12 gigahertz clock. Okay, and I have a requirement that I need these phases, the 12 gigahertz phases, to be phase aligned. Now the question is, if there are different path lengths, how will the phases align? Because there would be different delays over different path lengths. This is where the feature of digital modification within the outputs of the LTC6952 clocking IC comes into picture. What happens is, say I notice that I have this clock signal, that is clock signal number 1, reaching my clock IC at say 10 microseconds, okay, sorry, 10 milliseconds, and I notice that the second clock IC outputs a clocking signal and it reaches the clock signal at say 10.5 0.006 milliseconds. That is a difference of 6 microseconds. Okay. Now my question is, this 6 microsecond phase offset within the PLL ICs would basically get basically get fed into the 12 gigahertz sampling clock too, because what I just mentioned, just recall that my reference frequency and my sampling clock frequency would be phase aligned. So if this reference frequency is phase offset from one of there's a phase offset between the first and second clock outputs, then there would be of course a phase offset between my sampling clocks too, right? So how do I curtail this? How do I eradicate this 6 microsecond of phase error between my first sampling clock and my second sampling clock? What I do is I use my digital and analog delays to basically make the faster channel, which is the channel number 1. Basically I will use my digital and analog delays to put in a delay of close to something that is 6 microseconds, so that what happens is I'm forcing my first clock output, okay, to reach at a time of 10 milliseconds but delayed by further 6 microseconds, so that it also reaches at around 10.006 milliseconds, and therefore I achieve a phase synchronization between both of my reference 100 megahertz clock, that is this clock and this clock, and thereby I achieve phase synchronization between my 12 gigahertz sampling clock. And to develop on this is one of the most important parameters to achieve if you want to synthesize a larger system such as the quad MXFE platform, wherein we put in multiple 4 receive 4 transmit ICs to build a bigger system that has 16 receive and 16 transmit channels, all phase aligned. Okay, so this is very important. This is how we usually, this is a very simple application of achieving clock synchronization. I of course did not go into the depths of it, but like I just wanted to put in a picture in front of you all as to how we achieve sampling clock synchronization for all my converted ICs that I want to put in my system and have them synchronized on the basis of my clock. Okay, so with this I would like to conclude, and I am open for questions if there's any.
Hello, sir.
Hello, yes, tell me.
That was a very great session, sir. Very informative. Uh,
Yeah. So
Yes,
as we move into the
so
Q&A segment, please feel free to ask any question you have about our today's session. You may type your queries in the comment section.
guys, I'll be if there's any questions, I'll be getting them here, right?
Yeah, yes.
yeah,
Okay.
yes, sir.
I'd like to just mention something else too. A small achievement on our part is that analog devices has been very actively a part of ISRO's success in the Chandrayaan mission. There was a lot of parts that from analog devices that have been used, and presently, since I'm also working with ISRO to develop some of their applications, that is this satellite communication. So I would like to just make it a point that like analog devices have also been a part of like ISRO's success. And I would love to take questions from people who are interested in this domain.
Yes, sir. Definitely. So there's a question. What is the significance of Turing test in artificial intelligence? Vidyut
Oh,
Nomani has asked.
I am so sorry. I'm not aware of this. I am not into artificial intelligence much. Sorry, I won't be able to answer this question. So sorry with you. I'm not into artificial intelligence entirely.
Sir
Okay,
Chandana has
so
asked a question.
yes, implementing filter helps reconfiguring. What is the question? Okay. So, Chandana, if you could reframe your question, I don't understanding. Implementing filtering helps reconfiguring. Really. Okay. Do you want an explanation? Like, how does this help? Okay. I'll just explain whatever I understood. So, basically, what happens is when you implement a filter, right? So it's basically allows you to capture a frequency band of your interest. By capturing, I mean that it has a pass band, that is a range of frequencies that will be passed onto your signal chain, and a part of the frequency band that would be rejected. That means it would be attenuated. Okay. Uh, so basically, what happens is if you have a reconfigurable filter, what you can do is you can selectively pull out chunks of your frequency band, okay, dynamically. Say you have multiple I mean coefficients of FIRs ready. What you can do is you can program them one after other. Say you have a requirement of say 1 gigahertz to 2 gigahertz, or say a 500 megahertz passband. You can reduce this passband to say 200 megahertz, because you have a digital reconfigurable based reconfigurable architecture. So this is what I meant with filtering. I hope that it answers your question. Okay, how does an analog signal differ from a digital signal? Okay, so basically, analog signal, I mean, is basically continuous. Analog signals are in a way natural, because all are natural signals, right? Say our speech signals, say our voice signals, say whatever. There's audio, there's radio frequency. They are all analog, meaning that they are continuous in the time domain. But if we were to process these signals digitally, I would require infinite amount of memory to hold an analog signal. So what we do is we try to sample, say after a span of say, that is my sampling frequency. Basically, after a sampling time period, say at every 1 second, I pick up data points from my analog signal, and I would try to reconstruct them back in the digital domain, that is on my FPGA or my digital IC. So we ensure that we do not have any loss of information by theoretically keeping it within the Nyquist passband to prevent aliasing, and so that we are able to finally reconstruct our signal of interest. Okay, I hope this answers your question. And what is beamforming? Oh, so basically, say you have an antenna. Okay, now you would have noticed that we have large dish antennas, right, that are able to move around. Okay, these antennas can mechanically steer the beam, this meaning that by achieving motion through its motors, you can turn the antenna around, and wherever the face of the antenna is, that is your point of direction of your beam. But to achieve this electronically, what you can do is you can keep your antenna system mechanically settled down. You don't have to move your antenna mechanically, but through electronically changing your phases of your analog signal, which is coming from the baseband, you can shift your beam through the formula that I just said. I mean, it's a little complicated, but essentially this is what is going on. You electronically give phase shifts to steer your beam to a particular direction. Okay, thank you, Vidyut. I wish you a great day ahead too. And I missed a question, sir. How do analog filters work and what are their applications? Okay, so analog filters are basically that fit into the RF front end. They basically implement signal processing or filtering in the analog domain. That means you can input a continuous signal to your analog filter to output a continuous have a continuous filtered output. So this is how analog filters work. Okay. Oh, that's a very good question, Ani. What are some real world applications of phased arrays that are crucial, and how do they benefit these applications? The first is defense. Okay, say a lot. Okay, a lot of defense applications are basically concentrating on this phased arrays because, I mean, in radars, if you are able to steer your beam, you are able to scan your entire, say, region of interest, say your boundaries, that is your your international boundaries, your international borders. You are able to scan like without moving your antenna and in a very fast manner. And also like what happens is when these systems are built to be very dynamic, you can jump in frequencies, you can do frequency hopping, you can change your frequencies, you can settle to one frequency, then you can jump onto other frequencies, and clubbing these all with the ability to steer your beam electronically basically helps a lot in your tracking and your defense applications. And also like your satellite tracking is there, right? That is like through a very narrow pencil beam, this tracking ability basically gives you a lot of, I mean, a smaller resolution. That means a very pointed beam that is basically helps you to direct your beam, the communication, to only a very pointed and a very accurate location. So this is where like phased arrays are very useful.
So there was a question from my side also. So what
Yes.
is meant by modulation, and does it affect in communications or like from RF systems? Does modulation affect the actual output of the and signals or antennas?
Okay, modulation. By modulation, you are meaning there's those intermodulation products that I mentioned.
Yes, sir.
Okay, so essentially what is happening, since most of our signals, I mean, most of our systems are ideally have to be linear. And by linear, I mean that we do not have any higher order terms. But since you all know that my amplifier gain saturates, okay, this introduces a level of non-linearity, that is higher order terms. Okay, so basically I want a system that basically mimics y equal to mx. Okay, that it just is a linear system. Okay, so once this is a linear system, I don't have any higher order harmonics. But the moment I have higher order terms, say x square, x cube, okay, what happens is this x square and x cube basically, what is happening? It's basically frequencies getting multiplied. So if you multiply to sinusoids, what happens is there's a shift in my frequency domain. And if this intermodulation occurs in such a way that this shift in frequency domain makes one of my unwanted frequencies to fall very close to my wanted frequencies, that's where I call modulation to be problematic. So I'm unable to filter out. See, my analog filter would have a pass band. Okay, it might not be so narrow. So what would happen is this f2 minus f1 and f1 minus s2 might lie very close to my signal of interest to the point I cannot even like attenuate them outside through my filters. So that is where it is a problem. That's where intermodulation products are problematic.
Okay, sir. That was really a good explanation. All the doubts were cleared. As
Okay.
we conclude our Q&A session, we hope all doubts from the audience have been cleared.
Okay, there
So
are a
that
few more
brings the
questions. Okay. Okay, I'm just do we have time? I just want to take
uh,
one more.
yes, yes, sir, yes, sir, yes, sir.
Okay, so I'll take this question from Ani. Just this one, right? How is phased array contributing in the field of 5G and wireless communication? Okay, so basically, what I can do is like I can steer my beam towards my users. It's basically if say I find that I have a large amount of users communicating, it's a 30-degree from my antenna. I can steer the beam towards them rather than wasting my energy in propagating somewhere where there's no point of propagating because I don't have anybody receiving nor transmitting. So this is where a simple application where you can use your phased arrays. Okay, so there are a
So,
few
sir,
more
that
questions.
okay,
So
so you
can
can
you
take the questions.
Okay, sir, can you explain? And no need to call me sir. Okay, it's absolutely fine if you get me by my first name. That's absolutely fine. Sir, can you trade us in solar panel nuclear processes? I'm sorry, Ankit, I will not be able to comment on this. I don't usually work on power systems, so I will not be able to like give you a picture of solar panels versus nuclear energy.
Okay, so that
Okay.
was the end for the Q&A section. And thank you so much, sir, for coming here for the session. As a token of our appreciation, we'd like to present you with a small gesture of gratitude. Your presence at Epsilon 2023 has been invaluable.
Thank you, everyone. Thank you, the audience, for being there and for your wonderful questions. It was really an honor for me to speak today and take questions from you. I hope this interaction continues in the future too. And I would like to foster and answer any of the queries that you have beyond the session too. You can always shoot me an email with your queries, and I'll be happy to answer them to the best of my abilities. So thank you guys. It's been wonderful, really wonderful, and I really commend the effort that you've been putting to organize this Epsilon event. I hope you have many more successful events in the future. Thank you so much. Thank you.
Thank you so much, sir, for joining.
Thank you. Thank you. Thank you. Thank you, the audience, for joining. Okay, so that's all. So may I take leave for the day?
Yes, sir. Thank you so much for
Okay.
joining, sir.
Thank you. Thank you.
Gratitude towards our sponsors with their support, starting with HP, our technical sponsor. HP is an American multinational formation technology company headquartered in California that develops personal computers, printers, and related supplies, as well as 3D printing solutions.
Our streaming partner is StreamYard. On the StreamYard platform, you may broadcast over any social network directly from your browser. Before choosing the premium plans to gain access to the more features, it provides a free option that you may test it out.
Our social media partner, Get My Fest, which provides all the publicity for our event, reaches a large crowd. With that, we draw the curtain on what has been an extraordinary session. We thank you all the participants for joining today, and we hope this workshop provides you with a valuable insights into the world of system designs and space communication. Now it's time for testing your knowledge and understanding and uncertainty. Please drop your questions in the chat box.
Please drop in your valuable feedback in the given link in the chat box. Your feedback and suggestion will mold us to make more quality rich content further ahead.
Thank you all for being part of this event. I hope this hands-on session of all the three tracks really invoke deeper interest in these topics. See you all on the day three of panel discussion on all the three tracks, where you will hear deep insights from the numerous industry experts. Excited or you all to see there. Thank you so much.
Thank you so much, guys, for joining this session. We hope to see you soon tomorrow. Bye bye.